These are the answers to the Chapter 17 packet, Additional Aspects of Aqueous Equilibria. So Section 1 is entitled The Common Ion Effect. So we're going to take a look at 3 different solutions. The first solution contains 16.4 grams of sodium acetate dissolved in a total volume of 1 liter. To convert grams into moles requires looking up the information on the periodic table, and 1 mole of sodium acetate has a molar mass of 82.034 grams. So we have exactly 0.2 moles of sodium acetate. Sodium acetate is a soluble ionic compound, so it is classified as a strong electrolyte. And since it breaks up into sodium ions and acetate ions, the concentration of each of these ions is 0.2 moles per liter. Our next solution is 0.2 molar acetic acid. We are given the Ka for acetic acid. It is a weak acid, so it is a weak electrolyte. The expression for Ka involves H plus and acetate over acetic acid, so we have that Ka expression. And now we're going to calculate the concentration of H plus, acetate, and the pH of this 0.2 molar acetic acid solution. So we set up our Ka expression. We plug in the 0.2 on the bottom for the concentration of acetic acid. We solve for X, and X is not only the concentration of H plus, it's also the concentration of acetate, 1.9 times 10 to the minus 3 moles per liter. When we take the negative log of this value, we get a pH of 2.72. So now we're going to take a look at solution 3, which is prepared by mixing 500 milliliters of solution 1, the sodium acetate, with 500 milliliters of solution 2, the acetic acid. Now, since each of those solutions had a concentration of 0.2 moles per liter, when we combine these two solutions together, we're going to cut the concentrations in half. So we have 0.1 moles per liter of both acetic acid and acetate. We're going to fill in our rice table. Considering that there is some level of ionization of acetic acid, that amount is X. So we have minus X on the left and plus X on the right. And because Ka is small, we can assume that 0.1 plus X and 0.1 minus X are approximately equal to 0.1. This makes our math easier. Now we're going to solve for the concentration of H plus, or the hydronium ion. And that works out to be, because the 0.1 will cancel out, H plus equals the Ka, 1.8 times 10 to the negative 5. So when you take the negative log of this number, not only will you get the pH, which happens to be 4.74, this value corresponds to the pKa of acetic acid. So earlier, when we had a solution that just contained acetic acid, we had a concentration of 1.9 times 10 to the negative 3. And now we have a concentration of hydronium which is much less. So the really question here we're looking for is, why is this value so much smaller? Again, the title of this section is the common ion effect. So what would the presence of acetate do to the ionization of acetic acid? That's our question. Well, the difference in the concentration of hydronium in solutions 2 and 3 can be explained in terms of the common ion effect. Whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte ionizes less than it would if it were alone in solution. This can also be explained in terms of Le Chatelier's principle. You have the equilibrium for acetic acid, but now we're adding additional acetate ions, and that will cause the equilibrium to shift toward the left, thereby decreasing the concentration of hydronium in solution. Here is another example of the common ion effect. We have a solution of a weak acid, so 0.2 molar hydrofluoric acid, and then a few drops of 12 molar hydrochloric acid are added. Now, since hydrochloric acid is a strong acid, after the HCl is added, that's going to cause the value of the hydronium ion concentration to increase because we're adding more moles of a strong acid. But then the fluoride concentration is actually going to decrease. This is again because of the common ion effect. Additional hydronium ions will cause this equilibrium to shift toward the left, thereby decreasing the concentration of fluoride. The common ion effect is also observed in weak bases. Let's start with a solution of ammonia, a weak base. The Kb expression for ammonia involves the concentration of hydroxide and ammonium on top and the concentration of ammonia on the bottom. To calculate the concentration of hydroxide and ammonium and the pH, we'll go ahead and solve for X in a similar fashion to how we solved for X with a weak acid. And when we solve for X, we get that the concentration of hydroxide as well as ammonium is 1.9 times 10 to the negative 3. The pOH is the negative log of that number, so the pOH is 2.72, and the pH is 14 minus that value, which is 11.28. So what would happen if ammonium chloride is added to this solution? Well, of course, the ammonium concentration would increase, but as a result of this shift, according to the common ion effect, the concentration of hydroxide would decrease. Again, additional ammonium ions are added, causing the equilibrium to shift toward the left. And if we had a solution that contained equal concentrations of both ammonia and ammonium, we could fill in our Rice table with minus X and plus X, like we did before with the weak acid. Because Kb is small, we can assume that 0.5 plus X and 0.5 minus X are simply equal to 0.5. That makes our math easier. When we set up the expression for Kb, we plug in the values that we have. The concentration of hydroxide is equal to the Kb, 1.8 times 10 to the negative 5. So that is the pOH, 4.74 is the negative log of that number. That is equal to the pKb of ammonia. And since 14 minus 4.74 is 9.26, you can see that our pH has changed when we have a solution of both ammonia and ammonium. It has decreased the concentration of hydroxide because the pH was around 11 and now it's around 9. So we have decreased the concentration of hydroxide by the presence of additional ammonium ions. All right, section 17.2, buffered solutions. Solutions that contain a weak conjugate acid-base pair are called buffered solutions because they are able to resist drastic changes in pH when small amounts of strong acid or strong base are added to them. So of the following 8 solutions, the ones that would be a good buffer solution involve a weak acid with its conjugate base, or a weak base with its conjugate acid. So the problem with the first choice, HNO3, is that's nitric acid, which is a strong acid. And sodium nitrate is a neutral salt, so not a good buffer. Hydrofluoric acid is weak. The conjugate base of hydrofluoric acid is fluoride, so sodium fluoride is a good source of that ion. That would be a good buffer. The next choice involves chloric acid, which is strong, so not a good choice. The next choice involves a weak acid, that's acetic acid, but we don't have the conjugate base. We have sodium hydrogen carbonate, which although it is a weak base, those two substances are not related in a conjugate acid-base pair, so not a good buffer. Then we have ammonia, a weak base. It is paired with ammonium chloride, so there's the conjugate acid, so that's a good buffer. Our next choice involves a weak acid, hydrocyanic acid, and sodium cyanide. The cyanide is the conjugate base, so good choice. The next one's methylamine, which although methylamine is a weak base, and acetic acid is a weak acid, they are not related to each other in a conjugate acid-base pair, so not a good choice. Then finally we have sodium dihydrogen phosphate, and we have sodium hydrogen phosphate. That is a conjugate acid-base pair, so it is a good choice for a buffer. So I've answered question B, but I've also answered part C, justify the choices. A good buffer should contain, as I said, a weak acid and its conjugate base, or a weak base and its conjugate acid. Now we have the Ka expression. We're just rearranging this to solve for H+. So when we do that, we get H+ equals Ka times the ratio of HA over A-. So this particular equation is on page 707. And from this relationship, we see that the concentration of H+, and ultimately the pH of our solution, are determined by two factors: the value of the Ka for that particular weak acid, and the ratio of the concentrations of HA and A-. This is fundamental to why a buffer works. If we know the Ka, and if we can keep these concentrations of HA and A- relatively equal, we're going to set up a buffer where the pH is going to be approximately equal to the pKa, as long as these concentrations of HA and A- are relatively equal. Here you can see a diagram in which we have a buffer solution. HF and F- are the components of the buffer. So in the middle of that diagram, the concentration of HF starts out equal to the concentration of F-. And then they add either a strong base or a strong acid to this buffer, and we see what happens. If they add a strong base to this buffer solution, the hydroxide reacts with the HF, producing water and fluoride. This will cause the concentration of HF to decrease and cause the concentration of fluoride to increase. Now, if instead of adding a strong base, if we add a strong acid, then the fluoride ions will react with the H+ ions to produce hydrofluoric acid. That will cause the concentration of HF to increase and the concentration of fluoride to decrease. But remember, a good buffer has equal or roughly equal amounts of these two conjugate acid-base pairs. So as long as the ratio of HA to A- doesn't change very much, then the change in the pH will be small when either additional acid or base is added to it. When you're doing pH calculations for buffer solutions, you can use a very useful equation called the Henderson-Hasselbalch equation. You will see this on page 709. You will also see this included on the equation sheet for the AP exam. And it's typically written as A- over HA, but in general terms it's the log of base over acid. So pH equals pKa plus the log of the base over the acid. So if we have a buffer that contains both acetic acid and sodium acetate, since those two concentrations are the same, the log of 1 is 0. So the pH equals the pKa, and as you recall from earlier in the packet, the negative log of this particular value is 4.74. So when a buffer contains equimolar amounts, or the same number of moles, of both the weak acid and its conjugate base, the pH of the buffer is equal to the pKa of the weak acid. So here we have buffer solutions that contain both acetic acid and sodium acetate, but this time the concentration of the two components are not exactly the same. So in our first example, we have 1 molar acetic acid and 0.8 molar sodium acetate. Will the pH be higher or lower than 4.74? Well, considering the fact that we have a little bit more acid than base, it is logical to assume that the pH will be slightly less than 4.74. When we plug in these numbers into the Henderson-Hasselbalch equation, we get pH equals the pKa plus the log of base over acid. That's 0.8 over 1. And this gives us a pH that is exactly 4.64. So it is slightly less than the pKa. On the other hand, if we have a solution in which there is a little bit more base than acid, we would expect our pH to be a little bit higher than 4.74. And sure enough, when we do the math, again using the Henderson-Hasselbalch equation, we get pH equals pKa plus the log of 1 over 0.8, and this will give us a pH of 4.84. That's a good way of predicting the pH of a buffer, knowing whether you have equal amounts of acid and base or slightly higher of one component. Now we have a buffer that contains a mixture of ammonia and ammonium, and the pH happens to be 9.43. Let's start with the pKa of the ammonium ion. They're giving us the Ka. We take the negative log of that value and we get 9.25. But remember, the pH of our buffer solution is 9.43, which is greater than the pKa. Since our pH is greater than the pKa, that must mean we have a little bit more base, ammonia, than we have acid, ammonium. To figure out what the concentration of ammonia is, if we're given the concentration of ammonium as 0.8, let's plug in all the information we know into the Henderson-Hasselbalch equation. So we know our pH of our solution is 9.43. We calculated the pKa as 9.25, plus the log of ammonia, which is the base, over ammonium, and that happens to be 0.8. So we go ahead and solve for the concentration of ammonia. Remember that the opposite of log is 10 to the x, so we have 10 raised to the 0.18 power is equal to this ratio of ammonia and ammonium. We get ammonia is 1.2. That is consistent with the fact that we did predict there was going to be a higher concentration of base than acid. Now we're going to talk about two properties of a buffer capacity and the pH range. The buffer capacity is the amount of acid or base the buffer can neutralize before the pH of the buffer begins to change to an appreciable degree. In general, you want a higher buffer capacity by simply having a higher concentration of your buffer components. The pH range is going to be the range over which the buffer acts effectively. Now, buffers most effectively resist a change in pH in either direction when you have about the same concentration of weak acid and conjugate base. And they have a usable range that's defined as pH equals pKa plus or minus 1. So for example, if the pKa of your weak acid is 5, then your buffer range would be between 4 and 6. Here we have two buffers, A and B. They each contain a mixture of acetic acid and sodium acetate. But buffer A has a higher concentration of each component. As far as the pH of these buffers, because the ratio is the same in terms of the number of moles and the log of 1 is 0, each of these buffers will have a pH equal to the pKa of the acid. In other words, 4.74. So the pH of buffer A is the same as the pH of buffer B. However, buffer A does have a greater buffer capacity than buffer B because it contains more moles of acetic acid and acetate. So buffer A is going to be able to withstand a greater concentration of either additional acid or base added to it. Buffer A will last longer. If you kept adding additional acid or base, the buffer A would be able to hold the pH for a longer period of time. Here we have two acids, hydrocyanic acid and hydrofluoric acid. The pKa of hydrocyanic acid is 9.31. The pKa of hydrofluoric acid is 3.17. And remembering that the pH range is plus or minus 1 pH unit on either side of the pKa, if you wanted to make a buffer solution at a pH of 9, hydrocyanic acid would be a better choice because its pKa is closer to 9. The other component you would need to make this buffer is the cyanide ion, which if you had to add that to the solution, you might just find a source of cyanide. Perhaps sodium or potassium cyanide would be added to a solution of hydrocyanic acid to make the buffer. All right, here we have a calculation we're doing with respect to a change in pH. We're going to determine what happens when either a strong base or a strong acid is added to a particular buffer. So this buffer contains 1 molar acetic acid and 1 molar sodium acetate. The pH is 4.74. The volume of the buffer is 1 liter. Now if we added 1 milliliter of 10 molar sodium hydroxide, 0.001 liters times 10 moles per liter. That would give us 0.01 moles of hydroxide ions. So it's going to be the acetic acid that reacts with the hydroxide and it produces water and acetate. So after the sodium hydroxide has been added to the buffer, the new concentration of acetic acid will be slightly less than 1 molar. In fact, it's going to go down by 0.01. So we had 1 mole of acetic acid, now we have 0.99. That's our new concentration. And since the acetate, which initially we had 1 mole of acetate, that's gone up a little bit. Now our new concentration of acetate is 1.01. Let's plug in these values into the Henderson-Hasselbalch equation and see if our pH has gone up a little bit as a result of adding the sodium hydroxide. Well, yes, our pH has gone up slightly to 4.75. Now, if we had added that same amount of sodium hydroxide to 1 liter of pure water, that would have meant that the concentration of hydroxide was 0.01. The negative log of that is a pOH of 2 and a pH of 14 minus 2, which is 12. So think about that. We added the same concentration or the same amount of hydroxide to pure water, and the pH would have gone from 7 to 12. And yet, when we added that same amount of sodium hydroxide to a buffer, the pH only went up 0.01 pH units. So this proves the point that buffers can resist changes in pH when small amounts of either strong acid or strong base are added. We just did the calculation for a little bit of strong base. Let's go ahead and do the other calculation for a little bit of strong acid. So here we have 1 milliliter of 10 molar HCl. That corresponds to 0.01 moles of H plus ions. This will cause the concentration of acetate to decrease a little bit as it reacts with it. So now the acetate, which was 1 molar, becomes 0.99. The acetic acid has gone up a little bit to 1.01. If we plug in these values into the Henderson-Hasselbalch equation, we can see that the pH will go down just slightly to 4.73 when the acid was added to the buffer. And had we added that same amount of acid to 1 liter of pure water, our pH would have been 2. That's a pretty significant change from a pH of 7. Again, the buffer was able to resist changes in pH, whereas in pure water, that would have gone down 5 pH units. All right, this is our next section, 17.3, acid-base titration. In an acid-base titration, we have a solution that contains a known concentration, for example, a base, and we're adding that to a sample of an unknown concentration, so that might be an acid. The point at which the stoichiometric equivalent quantities of acid and base have been brought together, we call this the equivalence point. And this can be signaled by using an acid-base indicator that changes color, such as phenolphthalein. You can also use a pH meter to monitor the progress of the reaction, and that'll produce a pH titration curve. So in this setup, you might, for example, have a burette containing sodium hydroxide of known concentration. You might have a beaker containing hydrochloric acid of unknown concentration. The chemical that's in the burette is normally called the titrant. It's what you're slowly adding from the burette to a particular beaker or flask, and that solution is called the analyte. If you use an indicator, you would put a few drops of this indicator to the flask at the very beginning, and then when the color change occurs, you stop the titration. That's called the end point. If instead you use a pH meter, then it is possible to keep adding more titrant past the equivalence point, because you can just analyze the titration curve and find out when the equivalence point occurred. Here we have an example of a strong acid, strong base titration. We start with 0.1 molar sodium hydroxide and 0.1 molar hydrochloric acid. Now the flask contains 50 milliliters of hydrochloric acid. Our initial pH of hydrochloric acid would be the negative log of 0.1. So we start out with a pH of 1. And since 50 milliliters is 0.05 liters, multiply that by 0.1 moles per liter. We start out with 0.005 moles of hydrochloric acid. We're going to get to the point where we add 49 milliliters of our titrant. So that would correspond to 0.0049 moles of sodium hydroxide. Now we have not reached the equivalence point. In fact, we are 1 milliliter away from the equivalence point. There is excess HCl. We subtract 0.005 minus 0.0049. So this represents the amount of excess HCl, 0.0001 moles. The total volume is 50 milliliters plus 49 milliliters. That's 99 milliliters or 0.099 liters. So currently, we're 1 milliliter away from reaching the equivalence point. Our concentration of H plus is 0.0001 divided by 0.099. So we have a concentration of H plus of 0.001 moles per liter. The negative log of that is a pH of 3. So in the first 49 milliliters of this titration experiment, the pH has changed very slightly from a pH of 1 to a pH of 3. Now something rapid is going to happen to the pH. As we get closer to the equivalence point, it's going to increase dramatically. So from 49 mils to 50 mils, we have now reached the equivalence point because the moles of sodium hydroxide are equal to the moles of HCl that we had started with in the flask. And because we have a strong acid and a strong base, the pH is going to be 7 because the salt that we're producing, in this case sodium chloride, is neutral. So sodium and chloride do not affect the pH of the solution. So in the space of 1 milliliter, the pH has changed from 3 to 7. Now we're going to go past the equivalence point and see if the pH rises even more. So we're at 51 milliliters. We're 1 milliliter beyond the equivalence point. Remember, we had 0.005 moles of HCl. We've now added 51 milliliters. That's 0.0051 moles of sodium hydroxide. So the sodium hydroxide is excess. There's the amount of sodium hydroxide in terms of moles that we have excess. Our total volume is 101 milliliters or 0.101 liters. Our concentration of hydroxide, 0.0001, divided by 0.101. We take the negative log of that, and we get a pH of 11 since the pOH is 3. So again, in the space of 2 milliliters, our pH has jumped from 3 to 7 to 11. That's an incredibly rapid rise in pH as you approach the equivalence point and then you go past the equivalence point. So here is the general shape of the pH titration curve for the strong acid being titrated with a strong base. The pH starts out low. So from 0 mils to 49 mils, the pH only changed from 1 to 3. Then the pH changed from 3 to 7 in the next milliliter. Then the pH changes from 7 to 11 during the next milliliter. And then finally, if you kept going beyond the equivalence point even further, the pH would start to level out around 11 to 13. It starts to level out. So it starts out low, rises rapidly, and then finishes high. If we had started with a strong base and we had slowly added a strong acid, this pH curve would look very similar but just upside down. So the pH would have been high if we had begun with sodium hydroxide in the flask and then slowly added HCl. It would have then fallen dramatically, still had an equivalence point around pH 7, and then finished off at a low value. So before we move on to an example of a weak acid strong base titration, let's go ahead and summarize the features of a strong acid strong base titration. The initial pH of a strong acid is very low. As the titrant, the strong base, is added, the pH increases slowly at first and then increases rapidly in the vicinity of the equivalence point. At the equivalence point, the pH of the solution is 7 because the salt that is formed in a strong acid strong base titration is neutral. And then after the equivalence point, the pH of the solution is very high because of the extra strong base. Alright, so now let's take a look at weak acid strong base titration. We have 0.1 molar sodium hydroxide. We have 50 milliliters of a 0.1 molar solution of a weak acid, acetic acid. So because acetic acid is a weak acid, the pH of a 0.1 molar solution is not going to be 1. It should be greater than 1. Let's calculate the pH of 0.1 molar acetic acid. We use the Ka expression. We plug in the numbers that we know. In this case, we have X and X on the top, and 0.1 for the concentration of acetic acid on the bottom. We set that equal to the Ka, and we solve for X, 0.0013 moles per liter. That's our concentration of H+. We take the negative log, and the pH is 2.89. So yes, it's indeed higher than the pH would have been if we had started with a strong acid of the same concentration. Now let's move on to 25 milliliters of this titrant has been added. So we had 50 milliliters of 0.1 molar acetic acid. That's 0.005 moles. We just added 25 milliliters of 0.1 molar sodium hydroxide. That's 0.0025 moles. We still have half of our acetic acid remaining. We've now produced that same quantity, 0.0025 moles, of the acetate. Now this should sound familiar. Remember, section 17.2 was about buffers. We have a buffer solution right now with equal quantities of both a weak acid and its conjugate base. Remember that the pH of a buffer equals the pKa when the concentrations of the weak acid and the conjugate base are the same. So something really special happens at the halfway point in a weak acid strong base titration. We use the Henderson-Hasselbalch equation, and we realize that since the moles of the weak acid are equal to the moles of the conjugate base, at the halfway point in any weak acid strong base titration, the pH equals the pKa of the weak acid. You can see in this diagram from your textbook that a variety of weak acids are listed here with their titration curves, and they're being titrated with a strong base. At the halfway point in the titration, which is at 25 mils on this diagram, the pH of the solution is equal to the pKa of the weak acid. Alright, now we are at 50 milliliters. So we have reached the equivalence point. Earlier, the pH of the equivalence point was 7, but it's not going to be 7 here. Let's talk about this. We had initially 0.005 moles of the acetic acid. We've now added 0.005 moles of sodium hydroxide. So at this point, there's no more acetic acid left from the original amount. We have neutralized it. But we have not produced a neutral salt. We've produced sodium acetate. The number of moles of acetate is 0.005. The total volume is 100 milliliters, or 0.1 liters. and we have a concentration of acetate, which is 0.05 moles per liter. Now the acetate, unlike chloride, which is a neutral ion, acetate is a weak base. So remember that sodium acetate behaves as a base in solution, so this pH is not going to be 7. The net ionic equation for what happens when acetate reacts with water is that acetate reacts with water to produce hydroxide ions and acetic acid molecules. So this represents the Kb expression, if we write this for this reaction, and acetate is a base. So the Kb would be the Kw divided by the Ka, which works out to be 5.6 times 10 to the negative 10. Remember the concentration was 0.05. We plug that number into the Kb expression on the bottom. We solve for x, and we get the concentration of hydroxide is 5.3 times 10 to the negative 6 moles per liter. Take the negative log, 14 minus that value, and again you can see the pH is not neutral, it's not 7. The pH of this sodium acetate solution is 8.72. So we had to use a Kb calculation to solve that the pH is 8.72. If we go beyond the equivalence point, now the pH is going to rise sharply, and we've seen that before. So we have an excess amount of sodium hydroxide. That concentration and that pH work out to be 11, very similar to what we saw before with the strong acid, strong base. So when you move past the equivalence point, the titration curve looks very similar to the strong acid, strong base titration. All right, let's summarize and compare and contrast the pH titration curves for strong acid, strong base and weak acid, strong base. Well, a solution of a weak acid has an initial pH that is higher than the pH of a strong acid of the same concentration. We saw that in this example. At the halfway point, the pH equals the pKa of the weak acid. The rapid rise portion of the curve is smaller than it would have been for a strong acid, strong base titration. And then finally, the pH at the equivalence point is definitely greater than 7 because the salt that is produced at the equivalence point behaves as a base. But after the equivalence point, the titration curves for a weak acid and a strong acid should appear similar to each other. All right, let's go back to that diagram that I showed you earlier. Again, we're summarizing the differences between weak acid and strong acid. For a weak acid, the initial pH is higher than it would be if it were a strong acid at the same concentration. At the halfway point in the titration, the pH equals the pKa. And at the equivalence point, the pH is greater than 7 because the salt that is produced behaves as a base. All right, another type of titration curve that's important to take a look at is a polyprotic acid. Now here we have more than one hydrogen that can be removed. So initially, we have H3PO3, phosphorus acid. So at point A in the titration, we have phosphorus acid, and it hasn't been reacting at all yet with the sodium hydroxide. At the first equivalence point, the first hydrogen comes off. So now at point B, we have H2PO3 minus as the dominant species in solution. And at the next equivalence point, the second hydrogen has come off, and the dominant species is HPO3 2 minus. This information that I'm showing you in the packet can be found on page 720 in your textbook. All right, let's talk about acid-base indicators. The pH changes very rapidly as you get close to the equivalence point, and in this region, one drop of titrant can change the pH by several units. Ideally, the indicator that you choose should begin and end its color change anywhere on the rapid rise portion of the titration curve. So in this example, we have methyl red and we have phenolphthalein. Would these indicators be appropriate for strong acid, strong base titrations? Well, methyl red changes from red to yellow in a pH range of around 4.8 to 6, well, that's along the rapid rise portion of either curve. Or phenolphthalein changes from colorless to pink around 8.2 to 10. So either of these indicators would be appropriate for these titrations, since they would have a color change occurring in that rapid rise portion. In other words, one drop of the titrant might be enough to tell you to stop the titration, that the end point can be signaled very close to the equivalence point. On page 721, you can see the example that I just showed you. So using color indicators for titration of a strong base with a strong acid, both phenolphthalein and methyl red change color in the rapid rise portion of the curve. So when would an indicator not be appropriate? Well, take a look on page 721 and you can see that if we had used methyl red for a weak acid strong base titration, then the methyl red would have changed color from red to yellow at around pH 6. Stopping your titration before you reach the equivalence point would be a problem. So phenolphthalein is fine, since that color range is within the rapid rise portion of the curve, but methyl red would be inappropriate because the color changes before reaching the equivalence point. What if you had a weak base titrated with a strong acid? Well, now methyl red is fine to use because the equivalence point is around pH 5. But had you used phenolphthalein, you would have stopped your titration before the equivalence point. So again, you can see that the phenolphthalein would have turned from pink to colorless at around pH 8, and you're stopping your titration early. All right, this is section 17.4, Solubility Equilibria. In a saturated solution, there is an equilibrium between the dissolved particles and the undissolved solid. Write a balanced chemical equation for the equilibrium for the solid dissolving in water. So here's the example on page 723. Solid barium sulfate dissociates into barium ions and sulfate ions. Well, the formula of barium fluoride is BaF2. So the reaction involves the production of barium ions and fluoride ions. Notice the 2 as a coefficient for the fluoride. The formula for lead carbonate is PbCO3, and that dissociates into lead ions and carbonate ions. Then finally, silver chromate has a formula of Ag2CrO4 that dissociates to produce silver ions and chromate ions. Again, notice the 2 as the coefficient for silver. All right, now we have to write the equilibrium constant, but remember that a solid is not included. A pure liquid or a pure solid are not included in the K expression. So we have only the concentration of the barium and the sulfate ion, but we do not have solid barium sulfate in this expression. This is called the KSP, the solubility product constant. Using this as an example, for barium fluoride, we have concentration of barium times concentration of fluoride, and again, that's squared because of the 2 as the coefficient. Here we have, for lead carbonate, concentration of lead times concentration of carbonate, no coefficients, so no exponents there. And then finally, the KSP for silver chromate, concentration of silver squared because of the 2 as the coefficient, times the concentration of chromate. It is important to distinguish carefully between the term solubility, which is the quantity of a solute that actually dissolves to form a saturated solution, and the term solubility product constant, which is the number representing the equilibrium constant for an ionic solid and its saturated solution. So solubility has units of either grams per liter or moles per liter, representing how much can dissolve. KSP does not have units and is a constant for a particular equilibrium situation. The magnitude of the KSP can be used to compare the solubility, much like we did in chapter 16. The higher the Ka, the stronger the acid. We can say the larger the value of KSP, the more soluble something is in water. So silver chloride, silver bromide, and silver iodide are very similar chemical formulas, and the KSP values are given to us at the top of page 724. Whichever of these three values is the largest, in this case silver chloride, is going to be the salt that has the highest molar solubility in water. In a similar example, we have three sulfate compounds: barium sulfate, calcium sulfate, and lead sulfate. And these KSP values are found on page 1063. The largest of these values is the one for calcium sulfate, so that salt should have the highest molar solubility in water. So what can we do with the value of KSP and the information about solubility? Well, we can do a couple of things here. If you're given the solubility for an ionic solid, you can calculate the value of KSP. Let's look at example exercise 1710 on page 724. So they were given that the concentration of silver was 1.3 times 10 to the negative 4, and that was for a saturated solution of silver chromate. Now, based on the stoichiometry between silver and chromate, there's a mole ratio of 2 moles of silver for every 1 mole of chromate. So the concentration of chromate is half as much as the concentration of silver. Well, now that we know that number, 6.5 times 10 to the minus 5 moles per liter, all we have to do with these values is to plug them in to the KSP expression. But don't forget, we have to square the concentration of silver. So we have 1.3 times 10 to the minus 4 squared, multiplied by 6.5 times 10 to the negative 5, and we get a KSP of 1.1 times 10 to the negative 12. So here are three examples where we are given the concentration of one ion, and we have to determine the concentration of the other ion, as well as calculate the KSP. Now, the formula for copper, Roman numeral 2, carbonate, is just CuCO3. And because of that 1-to-1 mole ratio between copper ions and carbonate ions, if we're given the concentration of copper, then the concentration of carbonate is the exact same number. If we multiply these numbers together, because the KSP expression is listed as concentration of copper times concentration of carbonate, we get a value of 2.3 times 10 to the negative 10 for the KSP. Now, silver carbonate does not have a 1-to-1 mole ratio the way copper carbonate did. The formula for silver carbonate is Ag2CO3. So therefore, the concentration of carbonate is half as much as the concentration of silver. So that number is 1.25 times 10 to the negative 4. And we're not going to simply multiply these numbers together like we did for copper carbonate. We have to plug these numbers into the KSP expression, which means we have to take the concentration of silver squared times the concentration of carbonate. And if we do this math, we get 7.8 times 10 to the negative 12 for the KSP value. And then finally, our third example here in this table is copper, Roman numeral 2, hydroxide. The formula of that compound is Cu parentheses OH2. That means that we have twice as much hydroxide. So the concentration of hydroxide is twice as much as it is for copper. Then we go ahead and plug these numbers into the KSP expression. And don't forget to square the concentration of hydroxide. If you do this math, you get a KSP value of 4.9 times 10 to the negative 20. So we had just seen an example where you're given solubility and you calculate KSP. Let's go the other direction. If you're given the KSP, you can calculate the molar solubility. Let's look on page 725 at sample exercise 1711. They gave us a KSP value for calcium fluoride, 3.9 times 10 to the negative 11. We have an expression involving 1 mole of calcium for every 2 moles of fluoride. But we don't know what these numbers are, so we call them X and 2X. Plugging those numbers into the KSP expression, we have X, which is the concentration of calcium, times 2X quantity squared equals the KSP, 3.9 times 10 to the negative 11. So our expression becomes 4x cubed. X is equal to the solubility of this salt. We have to take the cube root of the KSP divided by 4, and when that math is done, we get 2.1 times 10 to the negative 4. That is the molar solubility of calcium fluoride. Now we could go on and do the number of grams per liter if we wanted to, but I'm just talking about molar solubility for right now. All right, our first example is lead chromate. That's PbCrO4. That's a nice simple example to start with because it's a 1-to-1 mole ratio between lead and chromate. So the molar solubility of lead chromate is X, and that's the concentration of lead. It's also the concentration of chromate. Since the KSP equals X squared, we just take the square root of 2.8 times 10 to the negative 13, and that will give us our concentration of both lead and chromate. And that works out to be 5.3 times 10 to the minus 7. Our next two examples are not as simple because of the ratio between the ions. So silver chromate, that's Ag2CrO4. We know the KSP. We don't know the concentration of silver and chromate. Let's let the concentration of chromate equal X, and that forces the concentration of silver to be 2x. Plugging those numbers for x and 2x into the KSP expression, now we get 2x quantity squared times x equals 4x cubed. So when we solve for x, this will be the molar solubility of silver chromate. And the concentration of chromate, which is x, works out to be 6.7 times 10 to the minus 5. So that number is the molar solubility of silver chromate. And the concentration of silver is just twice as much. So we get 1.3 times 10 to the negative 4. Now in our third example, lead fluoride is PbF2. Again, we'll have x and 2x for our concentrations of lead and fluoride. Plugging those values into the KSP expression, we have x times 2x quantity squared, 4x cubed again. Solving for x gives us a value of 2.1 times 10 to the negative 3. That is not only the concentration of lead, it's also the molar solubility of the lead fluoride. And the fluoride concentration would be twice that value, 4.2 times 10 to the negative 3. Earlier in this chapter, we talked about the common ion effect. We talked about how, for example, acetate can drive down the ionization of acetic acid, or the presence of ammonium ions will reduce the amount of ammonia's ionization. Here we have the same kind of situation for solubility. The common ion effect can apply in terms of the solubility. Another factor that can affect solubility is pH, because sometimes the salt is going to behave as a base, and it might become more soluble in the presence of an acid. Another factor is the presence of complexing agents, and we won't talk as much about complexing agents, but definitely we'll focus on common ions and the effect of pH. Now remember, in this last section, we had calculated the molar solubility of lead fluoride. It was 2.1 times 10 to the negative 3 moles per liter, but that was when it was dissolved in pure water. What is going to happen to the solubility of lead fluoride if we try to dissolve it in a solution that already contains a common ion? Well, if it already contains either lead or fluoride ions, the solubility of PbF2 will be less than it would be in pure water. Here we have an example for the solubility of lead fluoride in a solution that already contains lead and a solution that already contains fluoride. Before we do this particular problem, let's take a look on page 727 at sample exercise 1712. All right, in this example, they want to know what the solubility of calcium fluoride is in a solution that either already contains calcium ions or a solution that already contains fluoride ions. That's the common ion effect. We already know that the solubility is going to be less than it would be in pure water, but let's go ahead and do the math. So we set up an ice table, but instead of plugging in 0 for both calcium and fluoride's concentration initially, we start with 0.01 molar for the concentration of calcium. Now, we don't know what the concentration of fluoride is. We also know that there is going to be some additional solubility, so we call the amount that dissolves X. So calcium now becomes 0.01 plus X, and since we have a 2-to-1 ratio between calcium and fluoride, the amount that dissolves for calcium is X, but the amount for fluoride is 2X. This would be a messy problem to solve exactly, but fortunately it is possible to simplify matters. Even without the common ion effect, the solubility of calcium fluoride is very small. Thus, we can assume that the 0.01 concentration of calcium, which came from calcium nitrate, is much greater than that small additional amount. So we go ahead and make the simplifying assumption that 0.01 plus X is approximately equal to 0.01. We go ahead and do the math, and we get X is equal to 3.1 times 10 to the negative 5. This very small value for X validates our simplifying assumption, and again, we have much less calcium fluoride dissolving in a solution that already contains calcium ions than it would have dissolved in pure water. Let's go ahead and do the other example, which is the fluoride. Same kind of situation. We have plugged in 0.01 for the concentration of fluoride. And again, there's a plus 2x term, which we can ignore, and we get, we do the math, 3.9 times 10 to the negative 7. That solubility of calcium fluoride in a solution that already contains fluoride is much less than it was in pure water. All right, so we'll start with our lead. Here's our Rice table. We plug in the information into the KSP expression, making the simplifying assumption that 0.01 plus X is the same as 0.01. When we solve for X, we get 9.5 times 10 to the negative 4. So that is the molar solubility in a solution that already contains a certain amount of lead. If we do it for the fluoride, we plug in our information from the ice table, and we get 3.6 times 10 to the negative 4. So if we compare the solubility of lead fluoride in pure water with the solubility of lead fluoride in a solution that already contains either lead or fluoride, look at those numbers. It should be clear that the common ion effect is at work here. The solubility of lead fluoride has decreased because of the presence of a common ion. All right, so now I'd like to call your attention to a diagram way back in chapter 4 on page 128. Phillips milk of magnesia, which is magnesium hydroxide, is being added to a beaker, and it's very chalky because it doesn't dissolve in water very much at all. Then they added a little bit of concentrated hydrochloric acid, and all of a sudden the magnesium hydroxide becomes very soluble. Well, the reason why it becomes very soluble is because hydroxide ions were reacting with the strong acid, and that shifts the equilibrium so that now magnesium hydroxide is soluble, and you're actually getting a bunch of chloride ions as well. So the pH of a solution definitely affects the solubility of a substance whose anion is basic. For example, magnesium hydroxide becomes more soluble in water as the pH of the solution is decreased. So if a solution becomes more acidic and the hydroxide ions react with the H plus ions, that decreases the concentration of hydroxide, shifting the equilibrium toward the right, making it more soluble. Well, what about lead fluoride? There's no hydroxide in that formula. Is that going to be affected by pH? Yes. The reason why the solubility of lead fluoride is going to increase as the solution becomes more acidic is that the fluoride ion behaves as a weak base. So if any additional H plus ions are present, they will react with the fluoride ions to form HF, hydrofluoric acid. And this causes the concentration of the fluoride ions to decrease, shifting the equilibrium toward the right, making lead fluoride more soluble in an acidic solution. What about lead iodide? That depends on whether iodide behaves as a base or not. Fluoride is a base because it came from a weak acid. Iodide came from a strong acid, so iodide is not a base. Iodide is neutral. And as you can see on page 729, when they try to add additional H plus ions to a saturated solution of lead iodide, you don't get any additional effect of pH because the iodide is not able to react. So fluoride's a weak base, iodide is neutral. The solubility is going to increase if you have a weak base for your anion. We've got 5 substances here. Focusing on the anions, chloride, hydroxide, carbonate, bromide, and nitrate. How many of these ions, these negative ions, are bases? Well, chloride is neutral because it came from a strong acid. Hydroxide is definitely a base. Carbonate is a base because it came from a weak acid. But bromide and nitrate are neutral because they came from strong acids. So the only salts of this set that would be affected by having an acidic solution make them even more soluble would be the nickel hydroxide and the magnesium carbonate. All right, let's talk about the reaction of barium fluoride in water. So barium fluoride dissociates to produce barium ions and fluoride ions. Now let's talk about the reaction of hydrofluoric acid in water. Hydrofluoric acid, a weak acid, dissociates to produce H plus and F minus. What do these two equations have in common? Well, they both contain fluoride ions, so therefore let's see if we can combine these two equations together and produce the reaction for what happens when solid barium fluoride is added to a strong acid solution containing H plus ions. Well, it would look something like this. Barium fluoride is a solid reacting with H plus to produce barium ions and then molecules of HF. Using the KSP value for BAF2 and then using the Ka for HF. Now what I did here is I flipped the HF equation and I also multiplied it by 2. So I took the Ka value. It's going to be the reciprocal of the Ka squared. And so I got a new value for that particular reaction because I reversed it and I doubled it. When I add those two equations together, I get the reaction between barium fluoride and H plus ions. Now the K, the equilibrium constant, is going to be multiplying those two values together, 3.7. So what significance is 3.7? Well, that is greater than 1, indicating that this reaction would proceed spontaneously to the right, proving that barium fluoride is more soluble in an acid solution because of the presence of that basic ion, fluoride, and how the reaction would shift toward the right. All right, and then the comment about complex ions, you can see a table on page 732. Again, I want you to be aware of complex ions, but I'm not going to emphasize them in a major way in this particular unit. Section 17.6, Precipitation and Separation of Ions. You may recall, back in chapter 15, we compared Q versus K to decide if the equilibrium was present and whether it would shift to the left or the right. Here we have an example. We're comparing Q to KSP. Now, KSP represents the saturated situation. So if you're already at equilibrium, then your solution is saturated. If your Q is greater than KSP, you have gone beyond the saturation point, and you would have a precipitate form. If the Q is exactly equal to KSP, then you're currently at a saturated solution. You have the equilibrium. You're on the verge of producing a precipitate, but it hasn't happened yet. If your Q is less than KSP, then you are under the concentrations you would need, and no precipitate forms. So Q larger than KSP, yes, you get a precipitate. Q less than KSP, you don't get a precipitate. Let's see if Q is larger or smaller than KSP in this example. We have 25 milliliters of a solution of barium nitrate, and we have 25 milliliters of a solution of sodium sulfate. Now the spectator ions that we don't care about are nitrate and sodium. We care about the concentration of barium, and currently we have 5 times 10 to the negative 6 moles of barium ions. That would be a concentration of 1 times 10 to the negative 4 moles per liter. Another way you could have done this calculation is recognize the fact that 25 milliliters plus 25 milliliters, that doubles the volume, and it cuts the concentration of barium in half. So our new concentration of barium is not 2 times 10 to the negative 4, but rather half of that amount. In a similar calculation, you can get moles of sulfate. So concentration of sulfate is exactly half what it used to be in the original solution. We now know the concentration of barium and sulfate in our final solution, but is a precipitate going to form? Let's plug these numbers into the KSP expression. We call this Q because we don't know if a precipitate is going to form or not. When we do this math, we get 5 times 10 to the negative 9, which is greater than the value of KSP, so yes, a precipitate will form. In our next example, we're mixing barium chloride and potassium sulfate again. We have different numbers, different concentrations. Our concentration of barium in the final solution is 2.5 times 10 to the negative 6, and our concentration of sulfate in the final solution is 1.5 times 10 to the negative 5. Plugging those numbers into the Q expression, we get 3.8 times 10 to the negative 11. Now that value for Q is less than the value of KSP, so in this situation, a precipitate will not form. All right, let's decide if a precipitate is going to form. Is it going to be calcium fluoride or barium fluoride? So we're actually predicting which salt will precipitate first. Focusing on the value of KSP. What you should be aware when you look at these two numbers is that the KSP for barium fluoride is larger and the KSP for calcium fluoride is smaller. So what does that mean? Well, that means that the first salt that should precipitate is calcium fluoride because it has a smaller value of KSP. So we are slowly adding a 0.10 molar sodium fluoride solution from a burette into this beaker that contains both calcium ions and barium ions, and the first salt that should precipitate is the calcium fluoride. What should the concentration of fluoride be to get calcium fluoride to precipitate? We know the initial concentration of calcium in that beaker was 2 times 10 to the negative 4. We don't know how much fluoride there should be, so let's go ahead and calculate the concentration of fluoride that we would need. It's 4.4 times 10 to the negative 4 moles per liter. Now, you didn't have to do the following calculation I'm doing right now, but I'm going to go ahead and do it for barium fluoride just to prove a point. So I went ahead and calculated how much fluoride would there need to be to precipitate barium fluoride. Now you can see that 9.2 times 10 to the negative 2 is a greater number than 4.4 times 10 to the negative 4. So what does that prove? That the amount of fluoride I need to precipitate calcium fluoride is less. So that's the first salt that should precipitate. So that number is the minimum concentration of fluoride required to get the calcium fluoride to precipitate. So if I add this sodium fluoride solution slowly, I can keep the barium from precipitating and focus on the calcium since its KSP is smaller. All right, the last thing to calculate is, well, how much sodium fluoride would you have to add to reach this number? So we have a 1 liter solution that has a minimum concentration of fluoride, 4.4 times 10 to the negative 4. We would need 4.4 times 10 to the negative 4 moles of sodium fluoride, which is coming from a 0.1 molar solution. Let's use molarity as a conversion factor, and we get 4.4 milliliters of sodium fluoride solution would be needed for this calcium fluoride to precipitate. All right, well, that should be the end of the Chapter 17 packet. Thanks for watching, and I hope that my answers and explanations were helpful.